Okay, hi everybody. Hope you all can hear me. My name is Cindy. I'm with KEXAC. I'm the Assistant Director of Communications and Development. And I just want to welcome you to the third concurrent session of the day. This is from 1 p.m. to 2 p.m. and you are in science instruction, easy experiment students will love, with our program improvement specialist, Peggy Shearer. Just a few tips before we start. At the bottom of your Zoom screen, there should be a chat button that you can click that will open up the chat window. You can type in questions if you would like. Everybody is muted just because the feedback messes with the sound. So if you would like to speak up or ask a question, all you have to do is unmute yourself. And also, I think at the top of the Zoom screen, it might be different for different computers. There should be a place for you to choose which view you have. And if you choose speaker view, you can always see the speaker while the presentation is going on in the background if you wish to do that kind of view. So with that said, I will turn this over to Ms. Peggy Shearer and she will begin her presentation.
Hello, everybody. I appreciate you joining in with us today. I told Cindy before we started that I didn't have this cool little PowerPoint presentation that after watching all of these other people do, I may regret. So you're just stuck listening and maybe seeing me. So I apologize for that. But today we're going to talk about science. And the reason we're going to talk about it is having to do with making our students' education as comparable to any other student in the state of Kentucky as we can. We all know if you work in a KEXAC school that you have different kinds of students sometimes than other schools have. All of us have different kinds of programs, different students that come and go. There's just so many variables that you don't have in a regular school. And so it's important that we realize that we have to make lots of compensations, and I know you have definitely been working on that through all of this NTI kind of situation. But we need to make our kids as prepared as possible for whatever's going to happen to them when they leave us, whether they're going to return to their home school, if for whatever reason they are going to go to another KEXAC school, if they're going to work toward graduation, if they're going to go to college, whatever their goal is in life. And lots of times at this age, they don't know what their goal is. And so we have to prepare them so that they fit in with everyone else. All of you know stories of kids who have felt so deprived, I guess, of a quality education in some form or fashion. And sometimes that's their problem in terms of the fact that they didn't pay attention, they weren't interested in school. Others, it's because we as schools didn't provide the kinds of things that we should have for those students. And so what we're going to talk about today is science. And the reason I am talking about science today is because it is one of the 4 core content classes that every student should have every day, regardless of what kind of school situation they're in. But mainly because it is part of the new graduation requirements, which if you look at what the state standards now say for graduation, is that all students will take 3 science classes. But the kicker is that 2 of them are labeled as lab-based science classes. As KEXAC schools, I know that that has been a challenge for all of us. Now, I'll give you a little bit of background about myself. I taught 20 years in Wayne County High School as an English teacher. I was assistant principal at Wayne County High School for 3 years, and then high school principal there for 8 years. Retired, they opened a new girls residential facility just up the road from me, and so I worked there for 7 years. So regardless of where you are and what you're doing, I have been in at least somewhat of a similar situation to yours and can feel your pain or your joy in what's coming with the students that you have. And so with science, I feel like that we do not do nearly enough lab-based science information. And in saying that, we have very logical explanations in our heads about why we don't do it. And I want to talk about a few of them because I hope I can eliminate several of those from your mind about why you don't do lab-based experiments and how you can do them. One reason that we give ourselves is that I don't have a science degree. Hey, I don't have a science degree either. Matter of fact, very few people probably that are working in KAES schools have a science degree. And so don't use that as an excuse. You all had science classes in school. You all went to college. You had some science classes. So there are classes that are things that you will remember from those classes that will ring a bell with you and help you be better prepared than you actually think you might be. Actually, when I worked at Otter Creek Academy, I started doing a thing called Weird Wednesday. And to give my kids an opportunity to have some hands-on, some lab-based kinds of experiences, I did projects with them on Wednesday that were science-related. And that's what got me so interested in this science component, not being a science person, but because I found that interesting and my kids were thrilled to death. Instead of it being all computerized or it being teacher-led, it was things that I could involve them in some form or fashion. So you don't have to have a science degree. Another explanation we give ourselves about why we don't do a lot of science things is because we have this mixture of kids in our class that all have different backgrounds. Many of us have classrooms that have kids of all different age levels, taking all different kinds of science classes, whether it be 6th grade science or chemistry too. They're in lots of different places. And so in our minds, we're thinking, well, how could I possibly do science-based lab things when everybody's in a different place? There are commonalities in science as there are in anything else. And so to take just a few minutes once a week or twice a week and to do something that is lab-based oriented will be good for those kids regardless of what age level they are or what grade they are or what course they are signed up in, because there is so much overlap in what goes on in the science field. And as we go through some of these experiments today, I think you'll understand what I'm talking about. But don't use that as an excuse that all of my kids are different ages and different classes. Just go ahead and do the science labs. It will fit either with something that student has already had or something that that student will be having on down the road. So you can consider it an embellishment to their education, or you can consider it an add-on to something that they're already doing, or maybe a deeper level of something that they have already had in the past. Another excuse that we use, reason that we use nowadays is that there are restrictions for my kids as well. I can't have kids dissecting things. I can't have kids using chemicals. I totally agree. I totally understand. And I totally understand that you can't do those kinds of things. But there are thousands and thousands of things that you can do with your kids that will not have to be outside the parameters of those restrictions of your students. Well, when would I find time to fit that in? I've got to get all of this other stuff done. It's important that we not only prepare our kids for what's going on, but that we meet this graduation requirement of lab-based science. Is the lab-based science that we're going to provide going to be exactly what they would get in another school? Probably not. But at least we're making an attempt. We're breaking the iceberg off a little chunk at a time and exposing those kids to some kind of science labs, which is probably more than what we've been doing and what they have done in the past. The cost of things. We all know how limited our budgets are. We all know how tight that is. But the time of the things that we have to have, you know, where would I find materials for that and buy materials for that? The things that I'm going to be talking about are things that are very cheap, are things that you have at home, things that don't cost anything, and ways that you can do this very economically and very feasibly. Another reason that we say that we can't do lab-based science is that we have such transient students. If I put together 15 or 20, I'll have some kids that say, and oh, I've already seen that. Or I'll have kids that miss it and or the second part of something and miss it. The transient kid thing is not a problem because you can do things all throughout the year, and we'll try to, and KEXAC, we will try to help you with that. Time on task. It doesn't take too long to do most of the experiments that we're going to be talking about. There are things that you can do on a longer time frame, but there are things that are very short, you know, 3-5 minutes. Things that you can do that kids will be interested in, things that kids like to know about. Another reason that we could talk about would be that I don't know sources. I don't know where to find these things. I'm not a science person. I don't have any catalogs for this. I don't know where to look on the internet for this. Hopefully today we're going to give you some ideas about how to help that source situation. And the main factor that most of us have as a reason for why not to do this is that I just really don't have the time to put into adding something else to my curriculum that I have to do the work up front for. And hopefully today I can tell you how we can fix that problem as well. So I've given you some of the typical reasons that I in my head had as to why we can't use a lot of lab-based sciences. And I hope I've explained a few things about why we can eliminate those excuses or eliminate those reasons about why we are not doing more science-based classwork, and make it easy on you and easy on your whoever's going to be doing this in your school, and prepare you better to do lab-based science in your class. Now, I've said all that to say this. When we got graduation requirements and the State Department was talking about what they were going to do about that, that was one of the big red flags for me. How in the world are we going to do lab-based science class things with our kids? And so at KEXAC, we began to talk about things that we could do to help. And then COVID hit, and things just went haywire in terms of how everybody was doing things, and we were just trying to figure out how to survive. And so we began at KEXAC to talk about what we could do to help you all. And so one of the things that we decided to do was work on ways that we could do some science information that you guys could use, that we helped you provide. So I put together and pulled the information and did the work or whatever for almost 200 different science experiments that are easy, cheap, short-term, all kinds of good things that will be easy for you to do. So what we've done is we've put together material, and I did little short abbreviated versions of these little lessons for about 100 of them. And we are going to put those out to you in some form or fashion. We also put together the explanation about the materials that you need, the scientific explanation, some of the vocabulary, that sort of thing to go with every one of those lessons. So before too long, you should have in your wheelhouse about 200 science experiments or parts of science experiments with the information that you need that you can share with your students. It should be able to use with any grade level. You should be able to use them with anything that you choose to do in terms of time frames. So what we're going to do today then is show you a little bit of what we're talking about. And Cindy has put on the chat room over here the directions on how you will be able to get to these on the KEXAC website. So at some point you will want to copy that down, but at some point we'll send out some information too with all of the others, because what she's posting today is the 9 or 10 that we are going to focus on today. The rest of them we're still working on how to get in some kind of format that you can get to. So what she's posted in the chat section then is how we're going to get to these 9 or 10 that we're talking about today. She's going to show us the videos here in a few minutes, but what you're going to find on that page is the written directions about what you need, about how much of things, if you're going to mix something that needs to be accurate, and it will give you that kind of information. So Cindy, if you don't care, play that first little set of clips and then we'll talk.
Okay, first I just wanted to say that when we had first started planning this and Peggy was so kind to do this for us, um, we had like a professional videographer scheduled and everything, and we were gonna, you know, put on the lab coat and be in a real lab and do some Bill Nye stuff. But then COVID-19 hit, so Peggy was kind enough to have her niece, who is a photographer, help film these videos. And so that's kind of, and I was the one who edited them, and I have no background in editing, so bear with me when I show these. um, so that's where we are, and that's kind of what's holding us up on getting all these out. We need to kind of figure things out before we put it all out there. But anyway, I will go ahead and share the first video. If I can find it. No.
While she's pulling this up, you'll know that you obviously are aware that there are different categories of science. There's all kinds of biological science, all kinds of chemical science, all kinds of physical science, physics. And some of the things that I've done in these little clips are all, they may overlap with each other. So take a peek and we'll give you an idea of what we're talking about.
Is it, can you see it, Peggy?
I can see it coming up on the screen, but nothing's showing yet. There you go.
I brought an airplane plant. Some people call them spider plants. I'm sure that's not the botanical name for them, but I don't know what that one is. So that's something you could look up. But this airplane plant or spider plant has a lot of babies that hang down. So it puts up a stalk, and you can see this one has a pretty good plant here. And then it puts out new little babies all down the side. You can see the bloom here, and for each one of those blooms is going to produce a little plant. And that's how it propagates itself. So you can see that these hang down off of its plant. It's a hanging plant. And so what I did was took those that are hanging down, made myself a little tray of dirt here, and planted them. And you can see that very easily they're going to grow their own root system and be able to serve as individual plants. So off of this little plant, who's not very old, I probably got 20 or 25 little plants that I've already rooted that I can share with friends. So another way of doing propagation. The human body is just a very, very interesting thing in terms of how it works. We're going to look about how the human lung works. Now, I just have one here. Obviously, you know your lung has two different sections, actually 3 different lobes, but 2 on one side and 1 on the other. But how does it work? So let's talk a little bit about the lung. I've made a little makeshift lung out of balloons. And so we're going to see if we can blow that balloon up. And this sort of simulates what happens in your body when you breathe in, when you exhale and inhale. It gives you an idea about that it's confined to the amount of space that is available in your body. It also has an idea about that, you know, it can't get bigger than the space that is available there. But it shows you a little bit of a simulation about how the lung works. It would be easy to do one with 2 different straws and make 2 lungs inside of the tube for that matter. I enclosed the bottom just so that it looks more like a chest cavity, and the balloon couldn't expand any farther than the chest cavity would allow your actual lungs to expand. Very easy to talk about all kinds of lung disorders. Right now with the coronavirus going on, obviously that affects the lungs tremendously. You can't breathe as well. The capacity of your lungs is inhibited. Very easy to talk about that. There's lots of other things that cause lung disorders, things like smoking or all sorts of respiratory things. Even when you have allergies, your lungs are affected. So all sorts of things that you could talk about with the human lung. How many of you like yeast bread? I love yeast bread like this stuff here. It is delicious, but it's a process, and it's a chemical process actually, and so it would be an easy lesson to talk about with your students in terms of chemistry. So I have a half cup of warm water. It can't be boiling because it will kill your yeast. Your yeast obviously is a live product, even though it certainly doesn't look that way. So we're going to add to this yeast a teaspoon of granulated sugar, and we're just going to mix that granulated sugar up in that warm water to get it to dissolve. And again, that's even a chemistry lesson in terms of dissolving. Again, colloids and emulsions and those kinds of things would all fit into that category. Then we are going to take, and if you don't know what yeast looks like, those are live little fellows. They certainly don't look live, but what's going to happen is when they're added to the warm water, they are going to become live again. And they've sort of been in a state of stillness during that period of time that they've been in the package. And there's all kinds of yeast that you can buy. This one is Rapid Rise. There's a couple of different kinds that you can buy. So mix this together. And what we're going to do in this cup is we're just going to proof the yeast. Now, because yeast is a live product, sometimes it gets old and it doesn't cause the bread to rise, which is the whole point of doing yeast bread. Yeast bread starts out as something very flat. You mix it together. I've included a recipe in the notebook, and it would be easy for you to make bread with your students. But use the yeast. In 15 minutes, it will rise. You punch it down, and that's literally what it sounds like. You punch it down, let it rise a second time, and then put it in your pan, let it rise a third time, and then bake it. So within an hour, you can have a nice loaf of yeast bread like this one. But what we're going with this experiment is to talk about the proofing, to make sure that the yeast actually is alive and that it's doing its job, that I haven't left the yeast in the pantry too long and it has died as a result. So, by the way, there's directions on the back of the package that say how to keep your yeast alive. So interesting explanation back there about how to do that. So we're going to leave this for about 10-15 minutes, and then we're going to come back and look and see what happens. If the yeast is alive, then it will have bubbled and expanded similarly to what it does when you bake yeast bread. So this is the after effect. This is about 10 minutes worth of setting to give an idea. You notice we started out just with we put a little warm water. We put our sugar in it. Obviously, you need something for the yeast to eat. So you're feeding the yeast with the sugar, and we stirred that together. Then we added the yeast. Remember again that the yeast is a live product, which is always an interesting thing to me. And again, it tells on the back how to keep your yeast alive. And so this is the result to show that yes, this yeast is proofed and ready to go.
Okay, so as Cindy mentioned, obviously none of us are professionals that did this, but our effort and our attempt was to try to give you a springboard for what you can do with your students. None of these things that we put together are meant to be full lessons. They're there for you to get an idea about how simplified things can be. They don't have to be complicated. They don't take a lot of materials. They don't take a lot of time and effort, but they're very good for your students. I noticed somebody in the sidebar said food experiments are always a big hit, and yes, they definitely are. Some of my students' favorites of food experiments were making ice cream in a bag. Directions are in the notebook somewhere for that, about how to do that. Kids always love that. Making Coke floats. Obviously, root beer floats is a chemical experiment that you can do, talking about what happens when you put those two components together. Obviously, they love to eat the results of that. And probably my favorite student effort in foods had to do with crystal building. And there's tons of things that you can do in terms of crystal building. But in sugar crystals, we made the little sugar sticks that look like the candy that you can buy. And my staff probably didn't appreciate that I let them eat the sugar sticks, probably too much sugar overload. But they really enjoyed it, and it was something hands-on that they could actually do. Now, in looking at those three little things that we did very quickly, the first one obviously was something I had at home, cost me nothing. Okay, I had an old aluminum pan and some dirt, and made the first one. In terms of the plant propagation, there were hundreds of other lessons that could spin off of that. Things like asexual plant propagation. We could talk about seeds and developing seeds, let the students plant seeds and do some experiments about how to get those to grow, different experiments about light, all kinds of things to do with plants. You could talk about bulbs and how bulbs are different, how rhizomes are different than like irises, how rhizomes instead of bulbs. There's all sorts of different things that you can do in terms of plants. Again, things that you've got in your yard, things that you've got in your house, didn't cost anything. The lesson about the lung, I had taken a plastic drink bottle, 2 or 3 balloons, and a straw and some Play-Doh. So not things that you don't have around or things that would be very expensive. The dollar store and the Dollar Tree are my favorite places to shop. And so there's all sorts of things that you can buy in those places to help you with those kinds of experiments. There's lots of things that you can do in terms of body parts, and the lungs is one of those. There are several examples in the notebook of other things that you can do that have to do with lungs. The kids were much more knowledgeable than they thought they were when we began to talk about problems with your lungs, because they knew people that had to have a lobe of their lung replaced, or people that had a black lung, or people that had smoker's lungs. You know, so they're very familiar with lots of things that have to do with that. And probably my favorite thing that we did, my husband works at a meat processing place. And so they slaughter animals. And so I had an opportunity to get him to bring me some pig internal organs. And pigs are very similar to humans in many of their body organs. And so when the kids could physically see what the lungs look like, and they could see the different lobes, and I could point out the different lobes. And when I would blow down the trachea into the lungs and they could physically see the lungs expand, it really freaked them out. And so they could begin to see a little bit about how the human body works. And obviously, as I said, that bleeds over into all kinds of other topics that you could talk about in regard to that. The yeast experiment is one of my favorites. The proofing is pretty cool because the kids can see the reaction. There are lots of other things. As I said in the notebook, I included a recipe where you can do in an hour, do the whole process. They can watch the bread rise, punch it down, watch it rise again, and then watch it after it bakes. Then obviously they could eat the product. So the kids have always enjoyed anything to do with eating. I agree with that comment. So as I said, none of these things were meant to be standalone lessons, okay? If you use any of the little clips for anything other than inspiration, which is what my hope is, hopefully you're going to add some things to it. One thing being that you need to talk about the different types of science parts that there are, the chemistry, the biology, the physical science, all of those kinds of things. And even though we may not be doing the kinds of lab-based experiences that other students may be getting, at least they're having exposure. They can become familiarized with the scientific method. They know a little bit about the vocabulary, those kinds of things. So let's look at one more little clip, Cindy, and we're going to look at one more later, but let's look at the second one, and we'll look at 3 more.
Milk. Milk has some interesting properties to it. It does lots of interesting things depending on what happens with that milk. But let's look at what happens when you mix with Red Bull. And I mix with Red Bull not to gross you out if you're a Red Bull drinker, but to talk about the fact that Red Bull has an acidity to it, and obviously that acidity is going to have some different things to do with milk. So I just poured the Red Bull into this glass, and then I'm just going to add some milk. And you can see almost immediately how it is beginning to, what my grandmother would call clabber. But the casein is a protein that's found in milk, and groups of caseins, normally they just float around in the milk without bonding. But these groupings have a negative charge, and the acidity in the Red Bull causes the negative charges in the casein groupings to become neutralized instead of pushing each other apart like they normally would. The caseins start to clump together, causing the milk to curdle and form solid matter. And if we leave this for a few minutes, you would find that it curdles even more, and there will be a large pile of the curds on top of the milk. You can see they're almost coming up as we talk. So a few minutes to let this set would show you quite a bit more of the caseins in the milk. One of my students' favorites experiments is called elephant toothpaste. I'm not quite sure how it got the name. No elephants were killed in the making of this experiment, so I'm not quite sure where it got its name, but elephant toothpaste nonetheless. And so in the bottle, we have taken hydrogen peroxide, and you can use 3%, which is what you normally have at home. Or you can go to a beauty salon store and buy 6%, which is obviously twice as strong as regular peroxide, and you're going to get a bigger bang for your buck, I guess. So I usually use the 6%. It's obviously used for hair dye and so forth, so be careful what you're doing with it. But it is quite a bit stronger, actually double that. You can follow the directions that are in the book, but to that you're going to add a little soap. The soap breaks up the materials to let them work together better. We took a little yeast and added it to some water. That's what's in the cup over here. So in the bottle we have the peroxide, a little soap, and to that then we are going to add our little yeast and water mixture, a little squirt of soap in it already. And we are going to get elephant toothpaste. Obviously, we're talking about a chemical reaction here. And I put a little food coloring just so it shows up a little more. And you can see that you get a pretty good reaction. Whoops, pretty good reaction here. And that's because I've used that 6%. You can even see the steam coming off of it. So a pretty good reaction, and it's a very quick experiment to do, but obviously a good chemistry reaction with elephant toothpaste. Some people call this experiment invisible eggs. or naked eggs. Some people call them bouncy rubber egg. I've poured some vinegar into this container just now, and you can see that already the vinegar is beginning to penetrate the edge of the eggshell. Eggshells are porous. They will absorb things. Some of the egg demonstrations that we did talk about how the air pockets inside of the egg changes as it gets older, and as a result it will lay different in water to tell whether it's old or new, and it's permeable enough to let air in. That's what changes the air in it. But you can see very quickly that it almost immediately starts to change. Now what happens then is that it will literally eat all of the shell off of the egg. Now this one's been in for 2 days, okay, and you'll see that he will even bounce. Now, I did this with a boiled egg. You can do it with a raw egg. And if you do it with a raw egg, you can sort of see the yolk inside of it. And you probably can't see from there, but you can feel the air pressure has changed, and there's a little pocket of air on the end of that one. But this little fellow will bounce, which obviously you can't do with a regular eggshell, but the vinegar has completely eroded the eggshell off of the egg. And in some of the places, actually, you can sort of even see some of the egg shell that's peeling off. So interesting that you can have a bouncy egg, a naked egg.
Okay, so those 3 experiments, again, very cheap things. Obviously, the Red Bull experiment, just talked about some Red Bull and some milk. Most of you probably have the milk already. A little Red Bull doesn't cost too much. And most of our kids drink some Red Bull, or know people that do. And so, you know, when you mix the 2 together and you can see those casings coming to the top of the concoction that you've mixed together, my kids were like, ooh, what does that do in your stomach? So, you know, sort of interesting, makes them think, helps them to hopefully to remember about chemical reactions. The one that we did about elephant toothpaste, because of the volume of the toothpaste, it helps them remember that in terms of chemical reactions. Again, you can just use regular peroxide, a little soap, a little yeast. The yeast is, I don't know, $1, $2 or whatever for a line of 3 usually come together. And obviously, even if you buy the beauty shop kind of peroxide, it's only like $6, $8 for a large container that would do the experiment probably 20 times. So very cheap kinds of ways to do chemical experiments. There's tons of examples of egg experiments in the notebook. And I keep calling it a notebook. It's obviously going to be some kind of virtual explanation with all this information in it. I'm not sure exactly how that's going to roll out at some point. But the naked egg is one example. I've seen people do where they drop the egg off of a toilet paper roll on top of a pan and drop it into a container. You know, there's all sorts of egg experiments. All of you have eggs at home, or they're very cheap to buy. So all of those are cheap experiments. Now, in the notebook that I keep mentioning, there is an explanation about most of these things that we're going to be talking about. I've included several graphic organizers for the scientific method. I think it's very important that your kids learn about the scientific method. They need to know what an observation is, what a hypothesis is, about data and analysis. They need to know about a conclusion. They need to know about that scientific method. And so as you do these scientific lab procedures with them, please, please, please make sure that you are including the scientific method, because when they return to school or when they're doing something someplace else, you want them to be knowledgeable of the information just like the other students are, so that they feel comfortable and feel knowledgeable about what's going on. I want you to, and hopefully you will want to, discuss with the students what is happening. Talk about, I mentioned in the elephant toothpaste that you could see the steam rising off of that. Talk about that and what kind of observations they can make about why it exploded that much, about the steam coming off of it. And I've tried to include some scientific explanation for all of these things in the notebook. So I'm not asking you to go out and, you know, research hours after hours, but I've tried to include that stuff for you for the most part. Now, if I've not given you a good enough explanation, quite obviously you can YouTube anything and figure out what's going on, or you can Google anything and find an answer to those questions. Another important factor I think that you need to consider is that you need to make sure that you are adding vocabulary to things. You know, you can't just say, well, look at this thing and how this happens and this is an experiment. You need to talk about the vocabulary that's involved. Like I talked about the caseins in the milk. We talked about chemical reaction, talk about what makes a chemical reaction and maybe other examples of chemical reactions and what kinds of chemical reactions the students are familiar with. But think about vocabulary, and it's important to include that vocabulary. I hope you will expand and tie these to other lessons. These students are either doing some kind of book work that has science in it, or they're doing some kind of online courses that have science in it, and do some explanation about how that ties to what they're doing. Now, they may not currently be doing it in 6th grade, but when they see it in 7th grade, hopefully it will ring a bell. Or they may not be doing it in chemistry right now, but they remembered it from when they had it in something else. So hopefully you can tie it to lessons that they're already doing. As I would do Weird Wednesday, as I called it, at Otter Creek, the kids would say, oh, I just had that in my class the other day. Or I noticed that this chapter I've started on today talks about whatever term that we were using that day. And so kids can tie to that and expand on what they already know or enrich what they don't know about science. I hope that you will think about some way for you to help your students remember what they're doing. I would suggest them maybe taking notes, maybe have a little science notebook of the experiments that you're doing. And I hope you're going to give some kind of an assessment about them. Most students would see that as an opportunity to improve whatever grade they have in science. Lots of them, science is very difficult, particularly if they're having to do an online platform of science, because it's not something that most of us can give a very lengthy explanation for if the book didn't make sense. And so hopefully this would be a good way for you to add to grades that they are currently making and hopefully improve their scores. That gives them another initiative for remembering it, also gives them another incentive for paying attention with what's going on. So hopefully you will embellish this in your classwork with grades, maybe with a notebook. We are all aware that once you write things down, that's a good memory cue. Once you have to look something back up in your notes, that's another memory cue. And then when you've answered something on a quiz or on a test, that's a third time that that information has come up. So the idea of remembering those things is much more viable than if you don't give any kind of an assessment that goes with it. It's cool to watch elephant toothpaste explode, but at the same time, if they will remember on down the road what happened and the explanation for what happened, we're getting closer to what we're looking for with science lab experiments. These are just abbreviated lessons. I've just taken little short snippets of things. You will see in the ones that I've looked at that there's repetition of things. It would be easy to tailor the explanation of what you were doing to meet the age of the kids and do what kinds of things were important for each different grade level. You can pull from hundreds of different sources, but hopefully we're going to help you prepare for a lot of that. We should have enough information for you when we figure out how to actually get it to you that you should be able to do 2 experiments a week for the entire school year just based on the junk that's in this notebook. So that's not to say that there are not lots of other sources. Okay, Cindy, if you'll care, if you'll pull up that 3rd batch and we'll look at it.
of a very interesting phenomena to me. And it has to do with things like if you've ever been to the creek in the summertime and you see what we used to call Jesus bugs that sort of walk on top of the water. That's because the little pads on their little teeny tiny feet make a tension between the surface of the water, and that's why they don't sink. But let's talk about how that might work in some other things that you can see a little easier. Okay, so I've taken just a piece of tissue paper like you would use when you wrap something in for a Christmas gift or a birthday gift. And I'm going to put it in my cup of water here. And it's just going to serve as something for me to be able to use with my paper clip. Now what I'm going to do is hopefully that my paper clip is going to stay afloat instead of sinking. And the reason it's going to do that is because there is surface tension across the top of this bottle or this cup of water. Now I'm only putting this in here and then I'm going to sink it after I put my paper clip in. So there's my paper clip on there. Now, if things go well, when I sink this paper, my paper clip should stay afloat on my surface because of surface tension. There you go. Okay, surface tension again, a different experiment, same principle of surface tension. Again, there is a tension between the atmosphere out here and the water underneath the surface, and it causes surface tension. Now we've got a cup of water here, just plain water, and to that we are going to add pepper. Quite a bit so that it's obvious that you can see the pepper. And what we're going to do then is see what happens in terms of breaking the tension. Now, why does the pepper float? The pepper floats because there is surface tension in the cup. Okay, and that's why the pepper doesn't float. Now there are a few particles floating to the bottom. That's because they're heavier, they're not ground as lightly as the rest of the pepper. Now, if I put my finger in here, nothing happens except I get some pepper on my finger, all right? But if I add a little soap to my finger, okay, and then I touch in the middle of the pepper, look what happens. Watch closely. Why does all the pepper separate? Again, it has to do with surface tension. The chemicals that are involved in the soap, or the material that's involved in the soap, breaks up the cells that cause the surface tension between the water and the air. So again, we're talking chemical reactions. We're talking about what happens when you take something like a gummy worm, which is semi-permeable. You can get a little water in, but for the most part, they're not very permeable. So let's talk about what happens when you add different products to them. So we put some gummy worms in these, left them for 24 hours, and now we're coming back to look at what's going to happen to those particular products. So the original is here in front, or one similar to the original. And I don't know whether you can see or not, but they ate completely the little gummy bear that was in vinegar. Absolutely nothing left. This is a good example of how you can get students to make predictions about different reactions, as well as collect that data, come up with a hypothesis, and come up with a conclusion. So this is a good example for that. The second little gummy bear here, you can see, is that size. And then we've left Sprite, just some bottle of Sprite. You can see that he's lost his shape, but he has increased exponentially. You could even do weights or measurements with this to talk about how much they had grown. This one, the little green one, is salt water, and you can sort of get an idea. Oops, he's going to tear up in pieces and he's just going to be a glob. But you could very easily talk about how much he had grown, not nearly as much as the Sprite, but the salt water has grown as well. Alcohol is virtually the same size. Actually, I think he is the same size as when he started. So alcohol, you could talk about the permeability of that. Then this little fella is just plain tap water. He, like the Sprite, has grown. In my layman's opinion, he has grown even more than the Sprite has. So you could very easily talk about absorption. You could talk about things that dissolve and don't dissolve. You could talk about mixtures. You could talk about the molecules that hold that little gummy bear together. You could talk about water molecules, solvent. You could talk about gelatin mixtures, all sorts of chemical kinds of explanations for why gummy bears are what they are. Another egg experiment. This one is one of my favorites, one of my students' favorites. I'm going to take a bottle, and normally what I use is a Starbucks bottle. It does need to be the cold drinks, the Starbucks bottle. It does need to be so that the bottle is not, the egg will not fall down into the bottle to start with. You can see that I've used a boiled egg here, and the egg is not one that will fit into the bottle. My experiment is going to be, do you think that I can get this egg in this bottle? Interesting hypothesis. What do you think? So let's try it and see. I've taken just a few little pieces of newspaper. I am going to set them on fire. I'm going to drop them down in the container. And as soon as I do that, I'm going to set my egg on top of the jar, and you watch what happens. So I'm going to light my paper, set it on fire, drop it down into the container, put my egg on there. Voila. Now, why did that happen? It has to do with air pressure. Air pressure is one of the most unique things. It has to do with, in the bottle, there is air already. Obviously, you can't see air, but air is in the bottle. And so when I put the paper in there, the fire obviously has to have oxygen. So it burned off all of the oxygen that was in the jar. Then because the egg is malleable, it's changeable in terms of being able to squeeze a little bit. Then when there was no more air left in the container, then the vacuum started, and the vacuum sucked the egg down into the container. Now, if you watch Steve Spangler, who's one of the icons of science experiments, if you watch Steve Spangler, he will actually suck the egg back out. It takes 14.7% pounds of pressure to suck it back out. I'm not good enough to do that. So if you want to watch the egg come out of the jar, watch Steve Spangler on YouTube.
Okay, Cindy, if you don't care, go ahead and be pulling up the Steve Spangler one that I queued, and we'll talk about it in just a second. I appreciate Cindy putting in the safety measures. Obviously, you're doing things that with students. Make sure that you do safety procedures. You know, goggles, something for protection for your glasses in case there is any flying things. I wear glasses, so I didn't do that, but do take that into consideration. There are tons of other places that you can get information. As I said, we're going to try to roll out some things that will help you. I think Cindy's figured out a way to put some of these on YouTube for you. You want to explain that, Cindy, or?
We have a KEXAC YouTube account, and I'll be able to upload these videos that I've edited to there, and then I can figure that out. Yeah.
So these, the ones that we use today, you will be able to pick up on the KEXAC site. And then she gave you the KEXAC address that will have the paper version of explanation of how much of materials and so forth for the ones that we've done today. But I did want you to see Steve Spangler does fantastic things. You can YouTube all kinds of things for him. Bill Nye. There's a crazy Russian. He doesn't give much scientific explanation, but he's a good YouTube source for ideas. All sorts of things on Pinterest. You're welcome to follow my Pinterest account, which is under my husband's name, Gordon Shearer. If you want to look at the things I've marked on my Pinterest account, just hundreds of ways to do things. I did want to stick in this little Steve Spangler, obviously much more professional than mine, and we'll watch this experiment.
Five, 4, 3, 2, 1.
Please welcome our science guy, Steve Spangler.
This is hydrogen and oxygen.
Yes.
Okay?
Yeah.
So now scoop up some of those bubbles. That's perfect, right? So now I'm just going to light them on fire. Watch. Pretty cool. That's awesome. 7 feet long, 3 feet wide, about 2 feet deep. There's 2,500 pounds of cornstarch in here. Just go really, really fast. Ready? Go, 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 stop, don't stop, don't stop, don't stop. See what I mean? They dim the lights. We now put the electricity for the pickle. Look at that. Isn't that cool? Salt water is kind of the conductor of electricity. Yeah. And we're fine. See it?
There it goes. Back that no one will ever know.
Here we go. 4,538 nails. Your body. Isn't that cool? 3, 2, 1. Pour it in fast. Good job. So see that? Awesome. I'm going to scoop up a whole bunch of bubbles, and then you are going to take that lighter and light me on fire. All right? Now light this on fire. Here. Is that cool?
Get your smoke machine from at home and you just fill this up.
So now, if you tap on the thing on the bottom, watch what happens. Watch. Whoop. See? Yeah, go. So now, you can knock the cup. Okay. Wait, I have to smoke you again. Put it on. Okay, now talk to the audience.
All right, I will talk to you.
2, 1, pull hard. Nice! See? With nitrogen geyser. That's fine. Either one. That's okay. Nice. That's cool.
It's amazing.
Oh, I hope it will. Oh, that's awesome. Cool. No. Watch this. Awesome. 3, 2, 1. We should do this.
Wow!
That's fun.
That's amazing.
I like that.
That was so fun.
So obviously he has a lot better equipment, more money, and as somebody mentioned, a cleanup crew to go with that. But just to show you how exciting some of the things can be, even for us as adults, so you can imagine that kids would be excited as well. There's tons of other places that you can get sources. Steve Spangler does a lot of things on news shows. Some really impressive things that he does with them. You may have to look up the scientific explanation on some of those because, of course, he's short on time. Again, remember that we're doing this because the graduation requirements require 2 lab science classes. We need to make sure we're getting those in. Embellish what we're doing. We'll try to provide you with as much help and as much information as we can, and we'll get you some information out quickly about how to do that. Cindy's posting again the site where you can find that on the KEXAC website, and we'll be getting about 140 something more of them out to you before too long. So hopefully we'll help you with a way of doing this. And I've certainly enjoyed learning how to do all these experiments and enjoyed visiting with you today. If I can be of any help in the future, just let me know, and we'll be getting some information out to you soon about how to do these others. I don't know that I have answered all of your questions. Is there anything else that I can help you with today? Looks like she's looking for a way to email the link.
Yes, if you want to go ahead and type your email in there, I'll make sure you all get the link emailed to you as well. But also, we are going to upload all these resources to the KEXAC website. Probably next week, we'll have all the sessions that we've recorded and all the materials from the sessions that we do have available. And we'll post that on our website as well.
I hope what we've done for you has been useful. Our goal is to try to provide you from KEXAC as much help and as much information as we can to make your job easier, and hopefully that we can provide the best education possible for these kids that would be comparable to what they would get anywhere in the state of Kentucky or in the world for that matter. And we know that they have good teachers because I know many of you, and I know that we're working to provide that best opportunity for our kids. So thank you. Good luck.
Peggy, we do have one question in the chat that came through.
Yes.
Doug Elliott asked, do you know a magic number of labs or experiments that will satisfy the requirement?
I don't know that there is a number. I've never seen anything in the state requirements about numbers. My suggestion would be if you do 1 or 2 a week, that would be as much as what they would probably do in a regular school.
And also somebody asked about, will the digital notebook be available online? The one that I linked is just, again, the experiments that we showed in the videos today. And we are working on getting the full notebook together. It's just a lot. It's huge. It's going to be huge. And so we're trying to figure out the best way to do it and to get everything, you know, give credit where credit is due if we need to, and things like that. So that will be on our website as well when it's available. And of course, we'll send out that information in all of our KEXAC emails and things like that.
Okay, thank everyone for joining.
Thank you.